We've all looked up at the night sky, haven't we? And dreamed of traveling among the stars. But what if the biggest hurdle to getting there isn't, a bigger rocket or more fuel? What if it's something more fundamental, like our very understanding of the universe itself? And maybe the key to real space travel lies in a radical rethink of gravity, space, and time. Welcome to the deep dive. We're here to get you informed about the ideas that really matter. Today, we're digging into a pretty remarkable, though maybe lesser known work from back in 1956. It's called Steps to the Stars by Daniel W. Fry. And this isn't your standard science textbook, not at all. It's this unique mix of scientific ideas, some deep philosophical thoughts, and honestly, some really bold predictions. What makes it even more fascinating is the author, Daniel Fry. He was deeply involved in the whole mid century rocketry scene, but he came to some strikingly different conclusions about how we might actually reach the stars. So, our mission today, we want to cut through some, let's face it, complex ideas and maybe reveal a surprisingly accessible way to think about gravity, space, time, and how we could genuinely get out there. Not by brute force, see, but by understanding how nature is actually designed. It's about exploring what it means to truly understand, not just, no facts and formulas. Okay, so to really unpack these provocative ideas, we first need to understand the man behind them, Daniel W. Fry, born 1908. And he had some serious credentials, didn't he, in that early rocketry world? During WWII, he worked for Caltech, testing missiles for the military. He was also a charter member, a founder of the Pacific Rocket Society.
Yeah, and that's such a key piece of his background.
Yeah.
49 to 55, he was working for Aerojet General Corporation. I mean, at the time, that was the world's largest developer of rocket engines. Big deal. And it was during his time there, actually, in 1950, that this pivotal event happened. He wrote about it in detail in his first book, The White Sands Incident.
Hmm.
He claimed this experience basically showed him the severe limitations, the obsolescence, really, of the whole rocket concept.
Yeah.
And it brought him, as he put it, somewhat advanced and at the same time simplified concepts of the physical science.
So, yeah, he wasn't just some armchair theorist. He was right there in
Yeah.
the thick of it. And he didn't just write about it. He was active in related fields too, right? Like
Right.
superintendent of research at Crescent Engineering and Research Co. And he was also involved with this organization called Understanding, editor of their publication, First President.
Exactly. And his book's core idea is right there in the motto. When understanding is added to knowledge, it is but a step to the stars. Himmeling. Fry felt, really strongly it seems, that our scientific progress was being held back. We relied too much on what he called blind knowledge, knowing what happens, how it happens, the math formulas, but not really grasping why it happens.
He tells this great little story in the foreword to illustrate it about a kid who rolls a ball under the bed. The kid had been taught, from dust ye came and to dust ye shall return. So when he sees these dust bunnies under the bed, he runs to his mom all excited, Mommy, Mommy, come quick. There's somebody under the bed. He's either coming or going.
Yeah, it's a perfect little anecdote, isn't it? A bit of knowledge, completely misunderstood without real understanding. And Fry says, look, we all do that sometimes. We grab onto a little piece of information and think we got the whole picture. Or we'd get so tangled up in conflicting ideas we just, give up. His goal was simple understanding, to make sense of these puzzling mathematical laws.
And right from the introduction, Fry throws out a really provocative idea, this extraterrestrial connection. He claims contact between Earthlings and ETs isn't new, not at all. He says it's happened throughout history, usually when our civilization needed some help. Pretty bold stuff for a rocket guy.
It is bold.
Yeah.
And what's interesting is how he connects it to things like legends, like that story of the unknown man who supposedly helped break deadlocks during the forming of the U.S. Constitution, always offering simple compromises. He even quotes David Rittenhouse, the astronomer, from 1775, talking about infinite wisdom maybe stepping in to help created beings.
Okay, but the crucial part is his claim about the current visitations as he saw them. He dates them starting specifically in 1955, and he links this timing directly to when humanity realized, with terrible certainty, that we could actually destroy ourselves completely, the nuclear age. He even suggests these visitors basically achieved their purpose, leading to a tremendous change in international relationships by that same year, 1955. That's a huge claim. But, if this contact was happening, why didn't this advanced knowledge become, common knowledge? How did he explain that?
Right, good question. Fry's take is that people did receive advanced concepts from these contacts, but they struggled to communicate them to mainstream scientists. Not because the scientists were closed-minded necessarily,
Yeah.
but because there was no shared framework, no common reference points.
Yeah.
The way the contactee understood it or the way it was presented just didn't slot into the existing scientific boxes.
Okay. So that lack of a shared framework, that leads us right into Fry's really radical ideas, doesn't it? His whole reevaluation of physical law itself. We used to think physical laws were, well, linear, straight lines. They work the same everywhere, no matter the scale.
And that worked okay, for a lot of things. But then scientists started looking at the really small, the atom, the microcosm, and the really big galaxies, the macrocosm. And suddenly it seemed like different rules applied, different linear laws for different scales. It was disturbing. Einstein's great insight, as Fry points out, was realizing they weren't different laws at all. They were just different parts of the one great curve of natural law.
Right, like that surveyor analogy he uses. If you're just measuring a small house lot, you can ignore the Earth's curve. The air is tiny. But try mapping a whole continent. You absolutely have to account for that curvature. Fry says it's the same with natural laws. What looks straight on one scale reveals its curve on another.
Which brings us to maybe the most famous equation ever, EMC Teandra. We all learn c is the speed of light in a vacuum. Simple. But Fry challenges that. He says, hold on, the speed of light changes. It depends on what it's moving through. Think about a prism splitting light into colors. That happens because the speed changes for different wavelengths as they enter the glass. And even in deep space, there's always something, stray atoms, particles. So a perfect vacuum doesn't really exist. Our sole remaining constant, as he calls it, isn't truly constant in the way we think.
Okay, so if c isn't just the fixed speed of light, what is it, according to Fry? He argues c is actually the kinetic energy equivalent of the mass energy of matter. That's a mouthful. But think of it like this. Imagine you could convert, say, 1 gram of matter totally into energy. Then you use that energy to push all the rest of the matter you have, accelerating it faster and faster until it too converts to energy. The speed you'd reach at that exact point of total energy conversion, that's c. And it doesn't matter how much matter you started with. So c is more like the ultimate speed difference possible, the greatest kinetic energy differential between 2 points of reference, not just light speed. Kind of reframes the whole constant idea.
Exactly. And this ties into his bigger picture. Physical laws don't just go straight forever. They follow a curve, like a sine wave, a curve with peaks and troughs, positive and negative aspects. And crucially, points where a law might weaken to zero or even reverse its effect. It all depends on the context, the scale, the reference point. This opens up possibilities we wouldn't normally consider.
And nowhere is this more critical than with gravity. Fry calls it the greatest obstacle to space travel. We know Newton's law, universal attraction getting weaker with the square of the distance. But that leads to that paradox, right? If distance drops to zero, the force becomes infinite.
Right. Newton sort of worked around that by saying the force acts from the center of gravity. But Fry comes back with a really clear thought experiment. Imagine you could sink a shaft right down to the Earth's center. As you descend, your weight wouldn't increase infinitely. It would actually decrease. And right at the center, where your center of gravity meets the Earth's, you'd weigh nothing. Zero. Not infinite.
Zero. Why?
Because, Fry argues, gravity isn't just from the center point. It's inherent in every particle of matter. At the center, you'd have an equal mass of particles pulling you in every single direction. All those pulling forces would cancel each other out perfectly. Net force, zero.
Okay, that makes sense. But then Fry takes this even further, doesn't he? He suggests gravity isn't always attraction. That's the really radical part. He uses the example of uranium-235. You add one tiny neutron to its nucleus.
And boom. Instead of the internal gravity getting stronger, holding it together tighter, it flips. It becomes negative. Repulsion takes over, and the nucleus flies apart. That's fission. Fry calls this negative gravitation happening right there in the microcosm, inside the atom. Attraction becoming repulsion under certain conditions.
So if that can happen on the small scale, what about the big scale, the macrocosm?
Well, we have another paradox out there, don't we? If gravity is only ever attractive, the whole universe should be pulling itself together into one giant clump, like collapsing.
Yeah.
But what we actually see is the opposite. Galaxies are flying away from each other incredibly fast. Some are receding at over 25,000 miles per second.
Yeah. Astronomers came up with the Big Bang or Big Atom idea. Everything started in one super dense point and exploded outwards. But Fry points out a problem there, too. Under standard Newtonian gravity, a mass that huge would have gravity so intense, nothing could escape, not even light. A primordial black hole, basically.
So Fry applies his curved law idea again. He says, look, within a galaxy, the mass and distances are such that gravity acts as attraction. We're on the positive part of the curve. But across the vast distances between galaxies, the relationship changes. The curve dips below zero. Attraction flips to repulsion. That's why galaxies are moving apart and why matter isn't spread evenly but tends to clump together in galaxies separated by these huge repellent voids. It explains the structure we see.
Okay, so if gravity can be repulsive, what does this mean for getting to the stars? Fry says we've been thinking about it all wrong. We try to destroy gravity, shield ourselves from it, or just brute force overcome it with rockets. He says these approaches have failed or are just incredibly wasteful. He has that great comparison trying to propel a rowboat by throwing rocks out the back. Seems kind of absurd when you put it that way. And he calls the rocket concept itself basically obsolete for centuries, since Chinese rockets in 1214 AD.
Ouch. Yeah, he's pretty blunt about it. He says basically, it is time to re-examine our position. Have we forgotten the old saying, if you can't lick 'em, join 'em? The core question he poses is, what if we stopped fighting gravity? What if we started using it?
Using it, how? Like harnessing it somehow. He asks, what if you could put a spacecraft into that negative part of the gravitational curve relative to Earth? So instead of fighting to lift off, it would just fall away from the Earth as easily and as naturally as a stone dropped from a tower falls toward the Earth. That sounds amazing.
It does. But the immediate question is, how? If negative gravity only happens inside atoms or between galaxies, how do we create locally for a ship?
Yeah.
Fry uses this really helpful analogy. Imagine a simple bar magnet and a piece of soft iron. Normally they just attract, right? That's all an uneducated person sees. But wrap an insulated wire around that iron bar, run an electric current through it, suddenly you can make it repel the magnet. You haven't destroyed the magnetic field or shielded it or brute forced it. You've just polarized it. You've changed its local effect.
Ah, I see. So you're manipulating the field itself. And Fry concludes the same thing is possible with gravity. He states it's perfectly possible to produce a negative gravitational field between the Earth and a given object by the proper application of moving electric charges. And this field would only affect that specific object, not everything around it. The implications are just huge.
Yeah, they really are.
Yeah.
And thinking about manipulating fields like gravity naturally leads us to clarify some other fundamental ideas. Fry tackles, especially matter and mass. People mix these up all the time. Fry is specific. Mass is defined as resistance to change in the existing state of motion. That's inertial mass resistance to acceleration or deceleration. It's different from what he calls Newtonian mass, which is just the sort of inherent stuff in matter.
Okay, so inertial mass is resistance to change. How does that play out? He uses the electron example, right? An electron has mass, technically. But if you just held one and let go, it wouldn't fall unless maybe the ground had a positive charge. Its mass, Fry says, comes from its electric charge. When you accelerate it, you have to create a magnetic field around its path. That takes energy. The energy you expend to create that field is its inertial mass. So as it goes faster and faster, you need more energy. The magnetic field gets stronger. Its mass appears to increase, seemingly towards infinity as it approaches C. But crucially, Fry emphasizes this apparent increase is only relative to you, the observer.
Exactly. It's not like the electron itself is suddenly bloating up with infinite stuff. It's just that the energy difference between you and the kinetic energy differential is becoming enormous. It takes more and more energy from your perspective to make it go even a tiny bit faster. He uses this other analogy. Imagine firing a high-velocity bullet at a cork ball hanging on a string. The bullet might pass right through with little effect. But fire that same bullet at a massive steel block. It splatters, transferring huge energy. The bullet's effect, its apparent mass impact, depends entirely on the reference frame, the thing it hits. So this idea of mass increasing to infinity at c is just a measure of that energy differential. C is a limiting velocity, yes, but only relative to a specific reference point. It's not some absolute cosmic speed limit baked into the universe itself.
Wow, okay. So we've rethought constants, gravity, mass. What about space itself? Fry argues our definition of space might also be holding us back. Defining space is tricky. You have thinkers like Leibniz or Einstein saying it's about the order or arrangement of objects, or the common idea. It's just the emptiness where matter can be put.
Fry suggests a simpler, maybe more useful definition for understanding these concepts. Space is that which separates bodies of matter. Simple as that. And then he adds the crucial part. The degree of separation determines the degree of curvature of the natural laws between them. Space isn't just empty. It's the medium across which these curved laws operate.
So how does that compare to Einstein's idea of curved space? Fry takes issue with that, doesn't he?
He does. He acknowledges it works mathematically, incredibly well. But he argues it's very hard to actually picture mentally. It leads to paradoxes when you try. Like, if space itself is expanding, carrying galaxies with it, why don't we see the space between atoms in our bodies expanding? Or the distance to the moon increasing due to space expansion? It seems selective. Or observations suggesting the universe is expanding faster than light. How can space itself do that? It gets conceptually messy.
So what's Fry's alternative? Instead of thinking of space itself as being curved.
He suggests we should flip it. Think of space as the separation, and the natural laws operating across that separation as having inherent curvature. Exchange linear laws and a curved space for curvature of natural law operating in space. He felt this was easier to grasp intuitively, mentally picture, without losing the mathematical validity.
Okay, so curved laws, not curved space. That leads us finally to perhaps the biggest mind bender of all, time. Fry points out that our perception of time is our biggest handicap. We experience it as just one dimension, forward only. We can remember the past, experience the present, anticipate the future, but we only move forward. And that linearity, he says, really limits how we understand the universe's laws.
Yeah, his definition of time parallels his definition of space. If space is what separates matter, then time is that which separates events. And this relates to that tricky concept of simultaneity. When do two things happen at the same time? Einstein said, well, things observed simultaneously occur simultaneously for that observer, because any observation across a distance involves separation space, and therefore involves the curvature of natural law acting across that space. Your observation point matters.
And this is where Fry uses the incredible, detailed space travel analogy to really challenge our linear view of time. It's worth walking through. Okay, so imagine we build this super advanced ship, unlimited acceleration. We launch from Earth, heading for Alpha Centauri, about 4 light years away. The trip itself, let's say building the ship and the journey, takes 1 year of ship time.
Right. Now, as you accelerate past, say, half the speed of light relative to Earth, if you look back through your telescope, Earth's clocks would appear to be running at half speed. Things seem slowed down. Makes sense. Light signals take longer to catch up.
Keep accelerating. You reach velocity c relative to Earth. Looking back, everything on Earth appears to stop. Clocks freeze. Motion ceases. Time, relative to Earth from your viewpoint, loses significance.
Now, here's where it gets really wild. You accelerate past velocity c relative to Earth. What happens when you look back?
According to Fry, something startling. Earth wouldn't be in your rearview telescope anymore. It would appear in the forward telescope. It would look like you are now approaching Earth, not leaving it. And even weirder, everything on Earth would appear to run backwards.
Exactly, like watching a movie in reverse. A dropped ball falls up.
Well, why?
Because you are now moving faster than the light that left Earth earlier. You're catching up to light signals from Earth's past, seeing them in reverse order.
So let's say you average 4 times the speed of light on this trip. You arrive at Alpha Centauri.
Your ship's clock says 1 year has passed. Totally normal for you.
But looking back at Earth through this effect, you would have observed 3 years of negative time passing on Earth during your 1-year journey.
Which leads to Fry's punchline. We will arrive at our destination 3 years before we left the Earth.
Whoa. Okay, let that sink in. Arriving before you left. And from your destination, looking back with a powerful telescope, you could theoretically see yourself back on Earth, 2 years before you even started building the ship. And you'd also see your own ship appearing to fly backwards towards Earth in the distance. This forces you, Fry argues, to conceive of time as having more than just the one forward dimension we pursue.
And just to complete the picture, if you fly back to Earth, your astronomer friend, who watched the whole thing from Earth, he'll insist the round trip took, say, 10 years of Earth time, based on his observations of your light signals arriving. He'll calculate your average speed was maybe 45th C, not 4C. And the thing is, from each reference point, both accounts are correct. This highlights Fry's point. The so-called limitations of relativity are limitations of our perception, our consciousness bound by linear time. They aren't necessarily absolute limits for nature itself.
So, pulling all this together, what's the big takeaway? Fry seems to be saying these fundamental concepts, gravity, mass, space, time, constant state, they aren't the rigid barriers we thought. Our thought blocks, as he calls them, stemming from how we interpret the math, might be the real obstacles. Natural laws aren't enemies, they're potential friends if we just understand them properly.
Precisely. He emphasizes that the limits we find in our equations, they reflect the limits of our viewpoint, our way of measuring and perceiving. They have no absolute significance insofar as nature itself is concerned.
And this core idea, the sine curve nature of physical law, the idea that laws have positive and negative aspects, he says this isn't even a new idea, is it?
Not at all, according to Fry. He points to this ancient symbol found all over the world, a circle with a sine wave running through the middle. The circle represents the infinite universe. The sine wave represents the laws within it, curved, finite, with positive and negative cycles. He mentions seeing it in Chinese yin-yang, artifacts from the North American mound builders, texts like A Dweller on Two Planets. His critique is that modern science, in its focus on recent discoveries, has tended to discard or ignore knowledge just because it's ancient.
It's a fascinating thought. Our typical approach, maybe our instinctively aggressive nature, as he puts it, is to see a law as a barrier and try to smash through it or shield ourselves from it. But if laws have this dual curved nature,
Then if one pole or aspect of the law is hindering you, the other pole or aspect could actually provide the assistance you need. It's about working with the curve, not against it, like using the repulsive pole of the magnet.
so where does that leave us practically? Fry seems to think the theoretical heavy lifting, sorting out these misinterpretations, is kind of done.
Yeah, he basically says the ball is now in the court of the practicing physicists and engineers. It's time to apply this different understanding.
And the path forward for them isn't necessarily building better rockets.
No, he explicitly contrasts reaction propulsion rockets with what he believes is the future, field propulsion. He calls field propulsion the natural and universal means of producing kinetic energy differentials, essentially learning to create and manipulate those gravitational and lightly electromagnetic fields directly, like in the magnet analogy.
And then comes maybe his most audacious suggestion for how engineers might figure this out.
Right. He says their task will be greatly simplified if they don't just rely on theory, but if they actually study, well, spacecraft, which already exist and which have frequently been observed within our atmosphere.
Mm.
He directly references books like Edward J. Ruppelt's Report on Unidentified Flying Objects. Ruppelt headed the USAF's Project Blue Book, and Major Donald Kehoe's The Great Saucer Conspiracy. He's essentially pointing at UFOs and saying, look, the technology might already be here, let's study it.
That's definitely bold for 1956. Linking advanced propulsion physics directly to the UFO phenomenon.
It is, but it flows directly from his core arguments about understanding natural law differently. If you accept his premises about gravity, energy, and field manipulation, then, as he says, the age-old barriers of time and space will rapidly dissolve.
And Earthman will find that it is indeed only a step to the stars. Well,
No.
it really leaves you thinking, doesn't it? How much of what we see as hard physical limits are truly baked into the universe? And how much are just limits of our current understanding waiting to be expanded?